Hello students, this video we are going to show you how we can solve some problems, right? So if you remember, we were talking about harmonic function, right? So let's just say that Laplacian of u is 0, yes, and that is given by, so if you want to write it properly, it is basically in 2-dimensional. Let's just do it in 2-dimension. The higher dimensions are also exactly the same as I told you already. So essentially Laplace, okay, maybe I can write it like this is equals to 0 in the domain, and this is a very specific kind of domain. I will explain to you why it is required. Yes, so x is between 0 and a, and y is between 0 and b. Yeah, and here Laplacian of u is essentially uxx plus uxy, sorry. Yeah, okay, so that's the definition which you already know. Okay, now the point is this: see, in 3-dimension you just add uzz, on 4-dimension you add another one, right? So whatever I am doing it, we can do it for a higher dimensions also, no issues here. Okay, now there are some conditions which we will put here, which is u of x0 equals to f of x. I will explain to you what all of this condition means. Yes, and u of xb is equals to 0. Clear? And this is for 0 x a. Okay, maybe I can write it here a. Okay, and u of 0y that is going to be 0, and u of ay is going to be 0. Okay, let me do this thing and I will explain to you why we are taking this sort of boundary condition and why not something else. Yes, so y less than equal b. Okay, so first thing first, see, what we want to do is we want to solve this problem. Now this is a domain. Now here the thing is some remarks. I'm going to show you a method. Yes, and maybe I can put it in red. I am going to show you a method, and this method here, what we are doing is, this method is called separation of variable, which we have already seen in first order, right? The same sort of thing here we are going to do, but it is much more complicated here, and we'll see why we suddenly talked about the Sturm-Liouville problem and Fourier series in the beginning of the course, because we are going to need that. Okay, so the first remark is this: see, the thing is, the method works. Okay, the method works in rectangular domains. So does that mean that it does not work in other domains? No, it does not actually. Let's say if you have, let's say if you have a circle, okay, then you can have a polar coordinate, change of polar coordinate, right? And then what happens is it actually, moves the domain into a rectangular domain, and again you can use that. So essentially circular domains, rectangular domains, you can use this, yeah. If it is given you be an explicit rectangular domain, of course you can directly use it using x and y. If you are given a like a disk kind of domain, right? So a circle means disk. Yeah, let's just put it like this, disk. Then you have to use polar coordinates. Let's say if you are in 3-dimension, right? And in that case the rectangle in 3 dimensions, so in 3 dimensions this is a, so in b, let's say in 3-dimension, what happens is this rectangular domains get changed to a domain like this: ab cross CD cross EF, right? EF. So parallelepiped kind of domain, right? And in that case, let's say if you have now for a sphere, yeah. So what is the analog of disk in 3-dimension for a sphere? What you do? You use the spherical coordinate. Yeah. You already know what those are. So essentially in that case you have to do a change of variable. So these are the remarks. So essentially what's the point? The point is this: we are going to do this separation of variable only for what sort of domains? The domains which are rectangular domains, right? So in our case, you see x is varying between 0 and a. Let's just say this is your x and this is your y. So x is varying between 0 and a, y is varying between 0 and b. Okay, so that's your domain. Okay, and then this is the thing here. So this is your a comma b, that's point. Okay, so he said that y equals to 0. So see, this first condition, it says that, okay, the first equation, what does it say? Let's just call it 1, call it 2, call it 3. Okay, so first condition says that u satisfies Laplace u equals to 0 inside. So inside Laplacian of u equals to 0, we want to find such a u. along with that, there are some boundary conditions. So at the point x0 is essentially y equals to 0. This one, y equals to 0. So essentially this one, right? X0. There, u, if you restrict it to this particular line, then it is actually give you u equals to f. Clear? What about u restricted to, x equals to a line? So you see, x equals to a line, u is 0. So here u is 0. What about here? Here is y equals to b line, right? See, y equals to b line. X is u is 0. So here also u is 0. And here what is it? Again, u is 0. You see, this is this line, right? 0 y. Okay, so y equals to 0 essentially, sorry, x equals to 0 line. So I mean this line, so which is u equals to 0. Yeah. So what is the problem setup? The problem setup is this. We have a equation which is Laplace u equals to 0 inside the domain, inside the rectangle. And what are the boundary conditions? On one side of the boundary u is f, and every other point u is essentially 0. Clear? We want to find out, we want to see whether you can find a solution or not, and then I will explain to you why exactly, or maybe I can do it right now. Okay, so let's do that. See, the whole problem is this. So first of all, we are not changing in the domain. Let's say that the general boundary condition, how should it look like? So generally, so this is a part of the maybe remark. Yeah? See, the problem should look like this, right? Laplacian u equals to 0 in some rectangle 0a times 0b. Okay, so this is x, this is y. X varies in 0a, y varies in 0b. And you see, you can generally we write it like this, right? U restricted to the boundary. So let's say this is your omega boundary. U restricted to the boundary is, we are saying that it is some function g. Yeah. Now here you see, if in this case, if you look at this, this is the rectangle, right? This is the rectangle 0a and b, let's say. Yeah. Now you see what happens is here on the boundary is this line, this line, this line, and this line, and I'm saying g on the boundary. Okay, so you can think of it, this g, as g1 on this line, g2 on this line, g3 on this line, g4 on this line. Clear? Now you see, let's say if you solve this problem, let's solve this problem. So let's say that this line is your L1, this line is L2, this is L3, and this is L4. Clear? So your equation will look like this. See, Laplacian u equals to 0 and u restricted to L1. So the boundary condition I am restricting it is g. U restricted to, so basically g restricted to L1, and let's just call it that is g1. Yeah. See this g function, see this g restricted to the L1, and let's just call it the g1 function. Clear? Again, u restricted to L2 is basically your g restricted to L2, which is g2. Let's just call that. And u restricted to L3 is nothing but g restricted to L3, which is g3. Again, u restricted to L4 is equals to g restricted to L4. Clear? So which is g4. Let's just call that. I'm just defining stuff. So this is our equation. You see, this is the whole equation now. If we break that part up, so basically what is our original equation? It is L this in the omega, and u restricted to the boundary is g, right? Now the boundary is nothing but L1 union L2 union L3 union L4, right? So we are breaking up the boundary into 4 different sides, and on each side, when you restrict g to each side, let's just call that is g1, g2, g3, g4. Clear? Okay. And of course, we do it continuously. Yes, we do this breaking up in such a way that g1 and g2, g3, g4, if you just add it up, that is also going to give us g. Now you see, let's say that Laplacian of u equals to 0. Let's call this as maybe pi, pi. And in this interval omega is here 0a cross 0b. Clear? And I am saying that u restricted to the line Li. It can be this line, this can be this line, this can be this line, or this can line. So basically, I between 1, 2, 3, 4, any of this is essentially gi, right? For I equals to, let's say 1, 2, 3, and 4. So essentially, what I'm saying is this, that I am only giving the pi is that problem where Laplacian u equals to 0 on the inside, and u restricted to, so let's say p1 is u restricted to L1 is g1, but what happens to u restricted to the other points? U restricted to Lj. This is going to be 0 for I not equals to j. Clear? So essentially what I am saying is this. Let's say, so what does P4, let's say P3, this problem, how should it look like? It look like this. Laplacian u equals to 0 and u restricted to L3 is G3. What about u restricted to L1 or L2 or L3? That is going to be 0. Clear? So that is your Pi. Now you see, if we can solve this problem, let's say if we solve Pi and let me do it here. Let ui solves Pi. Then you see, if you define u, which is u1 plus u2 plus u3 plus u4, then what happens to Laplacian of u? Laplacian of u is Laplacian of u1 plus Laplacian of u2 plus Laplacian of u3 plus Laplacian of u4, and all of them are essentially individually 0. So this whole thing is 0. Okay, what about u restricted to the boundary del omega, right? What about that? So u restricted to the boundary is u1 restricted to the boundary, u1 restricted to del omega plus u2 restricted to del omega plus u3 restricted to del omega plus u4 restricted to del omega. Now you see, u1 restricted to del omega is g1 basically, right? Because that is the only part which is there. Every other part is essentially 0. So you do realize what is happening here is this, I mean u1 plus u2 plus u3 plus u4, this is g1 plus g2 plus g3 plus g4, right? Okay, so g1 is what? G1 is essentially, this is the whole function. So g1 is the function which is, I mean, you see here it is g1 and after that everywhere it is 0. That's the first problem. Yeah, so the function is g1 here and 0 everywhere. That is the first problem. So you see, u1 solves the first problem. So basically u1 restricted to the boundary should be g1, and then other one u2 restricted to the boundary should be g2, similarly g3, g4, right? So now you see, this solves the problem which is essentially our g. Clear? Okay, so this is the whole idea. Essentially what we are doing is we are breaking up into 4 parts the problem, and since this is linear, we can actually solve the whole equation like this. Is this okay? Right. So now with that in mind, let's just solve this problem. See, if we can solve this problem, and what we can do is, maybe for the second problem you can replace f with 0 and f here, f of x. For the next problem, so that will be p1. This is, let's say, p1. Any solution of this is p1. For the p2, you take this to be 0 and here you take f, and then this is 0, this is 0, right? That will be p2. And for p3, you take this to be let's say g of y, let's say, and every other lines it is 0. You understand? So you get p3, p4, and you get all the solutions, add it up, and then you will get a problem for general solution for this sort of problem. So essentially it boils down to solving this. Yes. Okay, right. So what do you do? So as I told you, we are looking for a non-trivial separable solution. Separable solution. What do I mean? You have already had an idea that we are basically looking for. One second, let me change this thing. So essentially we are looking for a solution which is u of xy equals to a function of x times a function of y. Is it okay? Once you do that, you can substitute, right? Substituting, we have that x double prime minus lambda x is equals to 0, right? Yes, and y double prime plus lambda y is equals to 0. If you substitute this in the equation, okay, let us see why it works. Let's say, what is u x x? It is nothing but x double prime of x and times y of y, right? Because this is independent of y, so essentially there is no x here, we can put it like this. And again, u y y is nothing but x of x, y double prime of y. Clear? Now you see, it is given that x double prime, so you see x double prime is a function of x, y, x is a function of x, y is a function of y. So I'm not writing this like this, I'm just writing it like this. So this is equals to minus x y double prime, right? If you put it in the equation, it looks like this. So what does that say? It says that x double prime, which is a function of x, by x is nothing but minus y double prime, which is a function of y, by y, right? And you see, this is equals to some parameter lambda. So basically a constant lambda, you can think of it like y, because, one second, this is a small mistake here, because you see, we are saying that the function of x is equals to a function of y. And that is only true if they are basically constant. Otherwise, it can't work, right? Okay. So it is basically lambda. And now, if you put it together, it means x double prime equals to lambda x of x and y double prime plus lambda y equals to 0. So that is how you get it. So what is lambda? Lambda is called the separation constant. Separation constant. Is it okay? This is how you get this two equation. Let's just call it star. Okay. Now, let's look at this problem more closely. Say that we take lambda to be, you see, the boundary conditions. Yeah. Since the boundary conditions okay, are homogeneous for x equals to 0, okay, and x equals to a. So we choose lambda equals to minus a square, and what happens is a positive, and what happens, the equation we actually end up is alpha square x equals to 0. So this is alpha square x equals to 0, and x at the point 0 equals to x at the point a is equals to 0. Clear? See what is happening here. What is the boundary condition? U at the for x equals to 0 and x equals to c, this is x equals to 0 and this is x equals to a, right? This is basically 0. X equals to 0 and x equals to a on this line is 0, right? So if you put it in the equation, let's again look at it. You see, u of x equals to 0, one second, u of 0y equals to u of ay equals to 0. This is given, right? So if you put it together, you see it becomes u x of 0 times y of y times y of y. This should be x of a times y of y, right? This is equals to 0. So x of 0 times y of y equals to 0. So it means x of 0 has to be 0. Why? Because otherwise, if y of y is 0, it means that your solution u has to be 0. But we have assumed that this is a non-trivial solution, right? So this is not true. Clear? Okay. So you get x of 0 equals to 0, and you also get x of a equals to 0 from the other part, this part. Yeah, that is the equation. Let's call this as 1. Okay. Now, you remember what this equation says, right? This is essentially your eigenvalue problem, and you can solve it. Yes, we all have already looked at it. So by solving it, yeah, this I am not doing because you already know this stuff, right? So if you solve it, it becomes n pi by a, right? N pi by a, and where n equals to 1, 2, 3, and it goes on. Yes. And what is the corresponding eigenfunctions? And the corresponding eigenfunctions xn of x will look like this: bn times sine n pi x by a. Clear? Okay. Again, I am not solving this thing because this is a eigenvalue problem. We already know how to do this. Yes, please do this and check. So this is an eigenvalue problem. Okay. So you have this alpha, you have this xn of x, right? Yes. Now what happens is this. See, this is using the two data which we have on the two lines. Yes, x equals to 0 and x equals to a. Now what happens to the other two data? Can we use that and do something? See, now we have actually solved for x. Now we don't know what happens to the y, this y. Yeah. Now we have to use that data here. So you see, it is given that y double prime plus alpha square y is equals to 0. So one second, let me just check. Minus alpha square y equals to, maybe I can write it properly. Again, y double prime of y minus alpha square y of y, this is 0, right? And what are the boundary conditions if you put it? You see, the one boundary condition is at the point 0. This condition is there. See, where is it? Yeah, u at the point, see, if y equals to b, u is 0, right? So let's just look at it. See, at y equals to b, u is 0. So essentially, x of x times y of b, this is 0. So that will give you again y of b is equals to 0. Why? Because x of x, if this becomes 0, then that solution turns out to be a trivial solution. So, and this is given y of b equals to 0. Clear? If you put that particular thing together, what is the solution of this problem? If you solve it and you get this solution, right? What is y of y? It is I'm just writing the short form with, maybe I don't know, maybe yes. Okay, it is of constant times sine hyperbolic alpha y plus another constant. Yes, where e and f are constants. Where e and f are constants. Okay, you can solve this thing, right? This is a very easy second order equation, and with this boundary condition you can solve. We are not putting the boundary condition right now. Without the boundary condition, this is the solution, right? Now if you put the boundary condition, yes, what you are going to get is, you see, alpha also we know already now. You see, this alpha we already know. You see, this alpha is n pi by a. Yeah, so if you put all of this together along this y of b, so check this part, please check this. Yeah, this I want you to check. Yn of y. Why yn of y? Because you see, alpha is not a single number, but there are like sequence 1 2 3 4 for every n there is a sequence. So alpha is like infinite sequence. So we have yn of y. For each alpha you have one y. So for alpha n you have yn. So that will be given by en. This doesn't get cancelled because you just have the solution, the information only at one point, right? So it becomes sine hyperbolic n pi by a y minus b. Clear? See, y at the point b equals to 0, if you put it there in the equation, this is what you are going to end up with. So please check this part. Check this part. I am not doing this thing. This is very simple calculation and I want you to do this. So please check this. Okay, check this. Okay, now once you check this, you see, because of the linearity, what happens is this. Because of linearity, see, xn, see, for a fixed n, let's say n equals to n naught. So x naught, x of n naught at x, y of n naught at y. This is x, u of n naught. So this is u of n naught at the point x and y, right? Yeah. You understand? This is one u which actually solves the equation. Yes. And now the thing is this holds for all n. So essentially, if you take the sum of it, that will also solve the Laplace u equals to 0. It has to, right? Because of the linearity. Okay. So what we do is, because of the linearity, we say that u of xy is nothing but the summation n equals to 1 to infinity, and then we'll put some constants here, an times sine n pi x by a, okay, and then sine hyperbolic n pi by a, and then y minus b. Clear? This is what we are getting. Yeah. Here where what is n? N is nothing but bn times en. Yeah, this en is there and that bn is there here. You see? So essentially, if you multiply it, those are the extra terms which comes out, and we're just writing it to be an. Yes. Now, see, we don't know what an is. We have to find that an. Otherwise, everything is done, right? How do I find an? You remember there is another boundary condition. What is the boundary condition? That u at the point, this boundary condition. Yeah. See, u at the point x0 is f of x. The first boundary condition which we have. So we are going to use this. We are going to use this boundary condition. U at the point x0 is f of x. Since u at the point x0 equals to f of x, this is given. So you see, if you put y equals to 0 in this, that should be satisfied. So it is n equals to 1 to infinity, an sine of n pi x by a, and then y equals to 0. So that will be sine hyperbolic n pi minus b by a, right? So this is basically your constant. You can think of it like this, and you have this summation of so this constant times this constant, and then sine of n pi x by a, the sum of this, you are writing it in terms of f of x. This is what This is nothing but Fourier sine series. So this is Fourier sine series, right? Fourier sine series. You see, we have to find what ANs are. Except that everything we know. How do you find ANs? So that is essentially your Fourier sine series. F is given to us and you want to write F in terms of a sine series, right? Once we can do it, then we can actually calculate what ANs are. Yes, I am not doing this part. I hope you can of course do this. Yes, please check this part. So ANs, yes, again, since we know already how to find out the sine series, we have already did it. I'm just writing it down. It is A times sine hyperbolic n pi b by a. This minus sign is because of this minus. Okay, and then 0 to a f of x sine n pi x by a dx. Is it okay? So that's your ends. Now, so what is the formal solution? How do you write down the formal solution? Therefore, the formal solution is whatever the solution is essentially. Yeah, formal solution is given by u of xy. Yes, what is it? It is given by summation n equals to 1 to infinity. Let us just write it down like n star sine hyperbolic. I will just put everything together, n pi by a and then b minus y. Yeah, and then by sine hyperbolic n pi b by a and then sine of n pi x by a. Clear? Where n star is this constant part. It is 2 by a 0 to a f of x sine n pi x by a dx. I hope this is clear. Okay, so this is how you solve the problem with one boundary data. Now now you have to do it for, let's say if you are given a general problem, you have to do it for 4 different boundary conditions and then add those 4 solutions, then you are going to get the whole solution. So it is a very big project essentially to solve one problem, but the thing is this actually works and it is not very difficult. Once you do it, practice it, it's not very difficult. I hope this is very clear to you. Okay, so with this I am going to end this video. Thank you.